Hi AP This is video 2 of our statistical analyses of the effect of lectin on mitosis in onion root. In our last video we learned a lot about different types of hypotheses, and actually today we're going to do our statistical test to see how we can test a hypothesis. So let's look at the test that we're actually going to learn about today. We're going to learn about the chi-square test. So the chi-square test is a type of statistical analysis, and it allows us to compare data between an experimental result and a control treatment. So it's only going to work when we have only two options. You either prefer something or you don't. You're either in mitosis or you're in interphase. So there's lots of different types of statistical tests, and chi-square definitely only works well when we just have two, like we have distinct categories. We don't have numerical results. We are either in this category or we're not. So let's take a closer look at this equation and break this down. So this x with the superscript of the 2, that is not x squared. I know it's weird. That is our chi-square test. So this is the value that we're actually going to be calculating, this x superscript of the 2. So that's the chi-square. How we will calculate that? We're going to have observed results, and those are going to be the results that we actually collect in our lab. The expected results are going to be always based off of our null hypothesis. And remember, our null hypothesis was the no effect, that we're not going to see any relationship between the independent and dependent variable. So when we do this chi-square analysis, we're going to see what we observed. We're going to subtract that from what we would expect if the null hypothesis was true. And then once we have that deviation, once we subtract those values, we'll square them, divide by our expected results, and then that crazy E is summation. We're going to add everything together. So a quick reason on why we do chi-square analysis. In biology, many times when there's drug analyses that are happening, they will do chi-square analysis to see whether or not that drug has an effect or it doesn't. If that drug does have an effect, they're going to always compare that to some type of treatment that will have no effect whatsoever. So often, excuse me, they will give some patients a drug and they will give other patients a placebo. So a placebo is something like a sugar pill or candy. It's something that the patient may think is a drug. It may be even something that the scientist might think is the drug. They might be a double-blind test where the scientist doesn't know what the drug is and what the placebo is either. And then we can get an actual result, because sometimes with human psychology, just the fact of taking medicine will make ourselves believe that we are feeling better. So that placebo is great to avoid that biases. So very often we'll do the chi-square analysis and we'll compare the actual treatment of a new drug against a placebo, and we'll test that null hypothesis, because if that drug had no effect, it should give us the same results that the placebo did. One thing that we're definitely going to have to look at today is we're going to have to look at our chi-square table. And what this has is critical values. So after we do all of our mathematical analyses, we're going to get a chi-square value. We're going to get a numerical result. Now, that numerical result is only important if we know what we can compare it to. So in biology, we know that we can never be 100% sure. We can never prove that something is correct. We can only reject a hypothesis. But we do have certain confidence levels, and biologists are happy with a 95% confidence level. If we're 95% sure that our results are valid, we're going to go ahead, we're going to publish that data, we're going to submit that, we're going to feel like that is a level that we're confident enough to link our cause and effect together. So what we have here in this chi-square table are different p-values, and those p-values are probability values. And the probability values are linked to that 95% confidence level. So notice that we have a p-value of 0.05 and a p-value of 0.01. AP Bio makes this difficult for no reason because biologists are always happy with a 95% confidence level. That means that we are 5% unsure, right? Because 100% minus 95 is 5%. So we're good with a probability value of 0.05 or 5%. So whenever you look at these chi-square values, you're always going to look at a p-value of 0.05. So that's nice because we're always going to look at this first row. This probability value right down here of 0.01, that would be if we were 99% confident. Now believe me, if you were 99% confident, yeah, definitely report that p-value. That's amazing. Do a happy dance. That doesn't happen very often, but in biology, we are fine with looking at p-values of a 0.05%. The next thing that we need to do to find our critical value is we need to know our degrees of freedom. Our degrees of freedom is going to depend on the type of experiment that we're looking at. And our degrees of freedom is always going to be our number of possible outcomes minus 1. So if we look back at this scenario here, we have two groups, right? We have the drug and we have the placebo. There's two possible outcomes here. So 2 possible outcomes minus 1, our degrees of freedom would be 1 in this scenario. So if I was looking at the results from a drug analysis test and I was looking at one drug compared to the placebo, I would look at a degrees of freedom of 1 because there were 2 possible outcomes. And then my p-value would be 0.05, so I would be looking right here at 3.84, and that would be the critical value that I would compare my chi-square value to. Okay, so let's look at this chi-square value in an actual example. So let's say that I have looked at this drug analysis. I've compared my results from the drug that I'm giving people to the placebo. And after I've done all of my mathematical equations, I actually have a chi-square value. Because I'm comparing 2 possible outcomes, a drug or the placebo, and then my degrees of freedom are my 2 possible outcomes minus 1, I know that my degrees of freedom that I'm looking at is 1. And then in biology, I also know that we're always happy with a 95% confidence level that translates to a p-value of 0.05. So the critical value that I'm always going to look at for this experiment would be 3.84. So let's say after I do all of my analyses, I get a chi-square value of 2.50. Remember, when we do the chi-square test, we're always testing the null hypothesis here. So a small chi-square value would support. Small supports, SS, small supports. So 2.50 is smaller than 3.84. It's smaller than my critical value. So if that would happen, that supports the null hypothesis. That supports that there's no cause and effect. There's no difference in the drug compared to the placebo. Let's look at the opposite of that. Let's say that I do all of my data analysis and my chi-square results give me a 4.50. When I would compare that to my critical value of 3.84, it's larger. If small supports the null hypothesis, large would say that I would reject it. Here's another example. Here's an example of pill bugs, and they're in a choice chamber. So if I put pill bugs right here in the middle of these two environments, they could choose, do I want to go to the wet environment? Do I want to go to the dry environment? There are 2 possible outcomes there. To figure out my degrees of freedom, that would be 2 possible outcomes minus 1. So my degrees of freedom would be 1. My p-value would be 0.05. So when I'm trying to determine the critical value for this experiment, it would also be 3.84. All right, so hopefully now you kind of have a better understanding of what the chi-square equation is. You also know what that chi-square table is of critical values and how to determine what you compare your chi-square value to in that critical value table. We're going to look back at this experiment that we looked at in our last video. So we're looking at the preference of snails. Do snails like to go upstream or downstream? And that is like 2 choices, right? You either like the upstream or you like the downstream. So there's 2 possible outcomes here. And just to remind you, our alternative or our working hypothesis was that the snails would favor upstream and we would find more of those snails when we recaptured them in the upstream environment. And our null hypothesis would be the no effect. Snails would have no preference. They don't care if they're upstream or downstream. And because of that, they're going to be pretty much relatively evenly distributed throughout the stream. So now we're ready to analyze data. So notice here that we have 2 streams that these experimenters collected data from. One stream was a sandy stream bed, one was rocky. So we have 2 data sets. We're going to look at this first data set together and we're going to do the math together. So everything that's in green right now, we're going to do together. You're going to copy those results down. You're going to put that into your lab report. And then the yellow results, those are the ones that you're going to do on your own. So let's just look at our green information first. And in that green information, we're looking at the sandy stream. And it says that 43 of the 50 snails were recovered upstream of their release point. So that's the actual data that we saw. Down here in the table, notice that I have my variable, and this is what was changed, or my independent variable, were the snails upstream or downstream. And then here are my observed results. That's actually what I would collect. That's where my dependent data would go. So let's go ahead and fill in that observed data right now. And notice that 43 of the snails were recovered upstream. It told me that there were 50 total snails, so the amount of snails that I recovered downstream would have been 7. So that's my observed data right there. My expected data, and I will say students always struggle the most with trying to figure out what the expected data would be. Remember that we are testing the null hypothesis, and the null hypothesis means that there is no effect, that the snails have no preference between upstream and downstream. So if we have 50 snails, and they're going to be pretty much relatively evenly distributed, we would expect half of them to be upstream, half of them to be downstream. We have 50 total snails. So there's 25 I would expect to be upstream, 25 I would expect to be downstream. Now, once we have those values, what I observed from my experiment, what I would expect if the null hypothesis was true, the rest is just easy math. So the first thing that we have is observed minus expected. So in our top row, we have 43 minus 25. That deviation will give us 18. And then in our downstream data, notice that that would be 7 minus 25. And that deviation will give us a negative 18. So don't be freaked out if you see negative numbers. That's very common in chi-square. In our next column, we have the observed minus expected squared. So that's 18 squared gives us 324. Negative 18 squared gives us 324. So if you get negative data, we're going to square it anyway. It becomes positive, so don't worry about negative data. And then finally, in our last row, we're now doing observed minus expected squared divided by expected. So that would be 324 divided by 25 because remember 25 is our expected value. So our upstream value would be 12.96. The same thing for our downstream, 12.96. And then finally, notice at the very end of that column, we have our x squared. Remember, that means chi-square. Chi-square means that we need to add all of those up at the end. So the summation of observed minus expected square divided by expected, I just add these numbers up. 12.96 plus 12.96 gives us 25.92. That's our chi-square data. That's our value. The math isn't that bad. But now what's important is understanding what that math means. So I need to compare my chi-square value of 25.92 to a critical value. So I need to first determine my degrees of freedom. I have two rows, two possible outcomes, upstream or downstream. So my possible outcomes are 2, subtract 1, my degrees of freedom is 1. And then the p-value that we use in biology is 0.05 because that gives me a 95% confidence level. When we look at that chi-square table, notice that we look at a degrees of freedom of 1 and a critical value with a p-value of 0.05 means that we're looking to compare our chi-square value of 25.92 to a critical value of 3.84. That's larger, right? Small supports the null, large rejects. So when you're answering number 6, the null hypothesis is rejected. That means that we support the alternative or the working hypothesis. Remember, we cannot say that we've proven anything. We haven't. Data can support something or reject. It can never prove. More importantly, you always need to include evidence from the lab to support or reject your conclusion. So all of this evidence from the lab will be your chi-square data, and then your critical value that you determine by looking at the appropriate p-value and the appropriate degrees of freedom. All of that has to go into your answer for number 6. Now you are ready to look at the calculation for chi-square in the rocky stream bed. So the rocky stream bed is everything that's here in yellow. You're looking at 22 of 28 snails recovered upstream. You're going to definitely do the math to determine how many are going to be downstream, and then you're going to fill out the rest of this table just like we did together. Your degrees of freedom are going to be the same. It's going to be 2 minus 1. And that means your p-value is always going to be the same in biology, which is 0.05. When you calculate your chi-square value and compare it to your critical value, then you will be ready to answer questions 7 and 8. Good luck, and I will see you in our next video.